I'll begin with a word of prayer. Heavenly Father, we thank you for the rain, and I thank you for the students and their interest in this topic. And I just pray that you just bless our work today, Lord. In your name I pray. Amen. I have a couple things to show you guys, and then I'll take your questions. So let's see here. First things first. It's bothering me to not show. Well, I guess you can. Fine. Let's see here. Example 5 in my. Well, I don't know what. I've called it example 5. Let me just call it example 1 for today, huh? This is going to get confusing for me. I write these stupid notes out, but I keep renumbering the stuff in class as I do it. It's going to catch up with me at some point. So I claimed that the center of the symmetric group was just the identity permutation. It's actually pretty easy to prove that. So let's suppose that sigma is a permutation in Sn. Now we do need n greater than or equal to 3, okay? And we want to assume that sigma is not equal to the identity permutation, right? So since n is greater than or equal to 3, there exists m and k in n sub n distinct, right? Because if we have if we have at least 3, we can pick 2 distinct numbers, right? And without, such that what? Such that sigma of m is equal to k. Now, why can I do that? We assume that sigma is not the identity permutation, right? Which means that it has to move something. So I'm just saying it moves m to k, where m and k are distinct. As long as sigma is not the identity permutation, that can be done, right? Then, as n is greater than or equal to 3, we can choose a third number, let's call it L, such that what? L, M, and K distinct, all right? You guys with me? And all you do is just sort of, this is almost what you just showed me, Emily. Your number 10 on mission 1 to prove that Sn is non-abelian. It's almost the same argument. So it's just kind of more symbolic, but we can construct tau, the cycle Lk. Yeah. And we're going to be able to show that sigma tau and tau sigma are different permutations because of what they do. Let's see here. So let's work it out. It's pretty easy. Sigma tau, and we'll let it act on, I think we do m. All right, versus tau sigma acting on m. If we can show that those are different, right? If two functions differ on their action on a single point in the domain, they're not the same function, right? So this suffices to show that sigma tau is not equal to tau sigma. And so let's see here. So sigma, and then what was tau? Tau was the cycle Lk, right? M. And so here we've got the cycle Lk. It acts on, what's sigma of m? Okay, right? So I'll do the last one first. K, you feed K into there, you get out L, right? What happens here? We feed m into the Lk cycle. This gives me sigma of m, right? Because Lk fixes m. M is distinct from L and K by assumption. And consequently, this is K, right? These are not equal. So, therefore, sigma tau is not equal to tau sigma. But sigma was an arbitrary permutation in Sn. An arbitrary non-identity permutation in Sn. We just showed that there exists another permutation, in fact, the transposition Lk, which it doesn't commute with. Consequently, sigma is not in the center of the group, right? So that implies then that the center of Sn only contains things which are not like this sigma. In particular, that is just the identity. Oh, I'm sorry. We use var epsilon for that, right? So it's unfortunate for the people who don't have time to watch this or come here But on the other hand, I do expect that they read the book. If you read the book and you try to adjust the section, this is old news to you, right? Because the argument I just gave is in the book. I'm just putting in my own words. Hardly that. The other thing I wanted to share with you guys briefly was the proof that the conjugate was actually a subgroup. That won't take us long. So if we have H is a subgroup of G, then I claimed that GH, G inverse was also a subgroup of G, right? For all G and G. That was a theorem. I forgot the number. But so the proof, let's just go through the, I mean, it's a great warm-up for today. Try to be fast with my stuff here so you guys have time for questions. So first of all, we're going to try to use the 1, 2, 3 subgroup test to prove it's a subgroup, right? So first of all, H is a subgroup of G, so therefore E is an element of H, right? And remember, what's GH, G inverse equal to? It's equal to G little h, G inverse, such that H is an H, right? And so what does that mean? So observe G, E, G inverse is what? Mm-hmm. So I feel like I did something there, but yeah, identity. So what does that say, though? That this is an element of the conjugate of the subgroup H, right? So E is in there. Step number 1 done. The identity's in our proposed subgroup. What's next? We should do what? Let X and Y be elements of GH, G inverse, right? So hence there exists, let's say, H1 and H2 and H such that what? X is equal to G H1 G inverse and Y is equal to G H2 G inverse. Multiply them, what happens? This proof's even harder to mess up, right? I could be really, really sleepy and still get this one spot on. It's really hard to mess this one up if you understand logic and the definitions and just proof, basic proof techniques. Yeah. Now, why is this? This is an element of the conjugate subgroup, GH, G inverse, since what? Right. Yeah, since H1, H2 is an element of H, as H is a subgroup of G, right? Exactly because H is closed under multiplication. So H1, H2. And then also, what's X inverse? X inverse is G H1 G inverse inverse, which by sock shoes is G inverse inverse H1 inverse G inverse, also known as G H1 inverse G inverse, which is an element of G big H G inverse, because H1 inverse is what? It's an element of H, right? Because H is a subgroup, it's closed under inversion. So there you go. 1, 2, 3. GH, G inverse is a subgroup of G, provided H is a subgroup. I would encourage you to work through the example in the section he gives about the conjugate subgroups of S3. Those are good calculations to do. Do you guys have any questions about that? I have that worked out if you want me to work it. Doesn't matter? Okay. I have one other example, not in Nicholson. I just think it's an interesting example. Then I'll take your questions. So the example is a matrix group example. What? It's just coming apart. This desk is losing its pieces. Let's see here. So here's a group. There's a group we could prove this is a group. Maybe that'd be a good exercise. SO2. All right. I'm going to make that. So what this is here's the definition I'm going to give for our purposes here. Cosine theta, sine theta, minus sine theta, cosine theta, such that theta is an element of the reals, right? And this is with the operation of 2 by 2 matrix multiplication. We can show that this is in fact a subgroup of what? This is going to be a subgroup of what I've called the GL2R. 2 by 2 invertible matrices, right? So if I pick cosine theta, sine theta minus sine theta cosine theta in SO2, well, I'm sorry. Let me say it a different way. Suppose that's A, all right? Let A be an element of SO2. Then A is like that, right? And what's the determinant of A? You see what happens here. Of course, 1 is not equal to 0. Right, so that's an invertible matrix, right? This is not a finite subgroup, right? So we can't use the finite subgroup test. We need to check 1, 2, and 3, right? No, so this, what have I shown so far? At this point, I've just established what? Yeah, so SO2 is a subset, right, of GL2R. That's the starting point. We sometimes forget this. Most of our examples don't really require any proof, but it is important that our proposed subgroup is actually first a subset of the group, right? There's actually something to check here, because GL2 is not just any old 2 by 2 matrix, it's 2 by 2 matrix which is invertible. Okay. So next, if we put theta equals to 0, right, what happens? I'll keep using A. A is what? What is this? This is sometimes called I2. That's the identity, right? So the identity is in SO2. So that's number 1, right? We got identity. Number 2, if we take cosine theta, sine theta, minus sine theta, cosine theta, and we multiply it by another such matrix, right? Cosine beta, sine beta, minus sine beta, cosine beta, like that, yeah? What happens when we multiply? I mean, it's trigonometry, but this works out to cosine of theta plus beta, the sine of theta plus beta, minus the sine of theta plus beta down here, and the cosine of theta plus beta here. That's not immediately obvious. Those are the adding angles formulas for sine and cosine respective. This is not surprising because this is a rotation by theta. It's the matrix of a rotation by theta. This is the matrix of a rotation by beta. And what happens if you successively rotate first by beta and then by theta? It's just like rotating by, or just, right? So this is a rotation by theta plus beta, right? Not surprising, really. But there you have closure, because of course theta plus beta is a real number if theta and beta are real numbers. And then 3, I think you kind of know what the inverse is, right? What's the inverse of a rotation by theta? I'm writing it in its rather unsimplified form just to emphasize the geometry of it. the inverse of a rotation by theta is a rotation by minus theta. In other words, if I rotate clockwise 30 degrees, pi over 2, sorry, what was I saying, degrees, don't tell Dr. Scamortis. If I rotate theta by pi over 3, then of course the inverse is counterclockwise by pi over 3, then counterclockwise. Reverse the clocks. Anyway, so, but the fact that this serves as the inverse is immediately clear from what's up here, right? Because if I put beta equal to minus theta, I got cosine 0, sine 0, sine 0, cosine 0, which is 1, 0, 0, 1, which is the identity. So there you go, 1, 2, 3. In fact, yes, SO2 is a subgroup of GL2R. I think this example, this kind of example is missing from Nicholson, and in fact most abstract algebra books, which is unfortunate because they belong. I mean, there is an abstract algebra book which has a lot more of this, called, I think, Herstein, but then that has its own set of problems, so I don't know. I actually know yet another subgroup of this group. Can you guys tell me what it is? What would a subgroup of SO2 be? SO1? That's funny. No. What is SO1 is a good question. Yeah, okay, I'm going to resist that. So no, how about this H? I'll just call it H. Hn equal to, how about this? And just for the sake of not writing all this junk again, let me just say that this is an A. This is a rotation by theta. Let's invent some notation for it so we don't keep writing that. So how about this? R of, I don't know, R of theta, right, in, SO2. This is kind of redundant given what I just said notationally, but okay, there it is. Such that what? How about this? Theta is equal to 0, 2 pi over n, 4 pi over n, n minus 1 times 2 pi over n. So here, basically another way to write that would be, oh, come on. How dare you? What on earth? Sounds really... Come back to life. Come on, come on. Come on, come on. All right, fine, I give up. Oh, that was sad. All right. How about this? So, there's some kind of, it didn't write, but it left some sort of like gelatinous ooze on the board that I'm walking all the way over here for this. Not a good sign. Try again. So this is actually theta is equal to 2 pi j over n for j 0, 1, n minus 1, right? Now, that is a finite set. So it suffices to show closure to prove this is a subgroup by the finite subgroup test, right? And so, if we take r of 2 pi j over n, and we multiply it by r of 2 pi k over n, this will give us r of 2 pi j plus k over n, right? Now, is that again, where is that? It might not be in our, that's not here necessarily, right? But what we can do is we can say, okay, so j plus k is equal to what? By the division algorithm, it is q times n plus r, right? Where 0 is less than or equal to r is less than n minus 1, right? And then if we look at the rotation by 2 pi j plus k is actually qn plus r, what do we get? Notice the n's cancel, so we get 2 pi q plus 2 pi r over n. But by the 2 pi periodicity of sine and cosine, this is just equal to the rotation by 2 pi r over n, right? Where r is in the necessary range, so this is an element of Hn again. Therefore, Hn is closed, therefore Hn is a subgroup. Can you tell me what this subgroup is? Let me ask it a different way. What group is this subgroup isomorphic to? I'll leave that open for now then. We've actually been studying 2 other groups in many times, many examples, many discussions, which are isomorphic to this group. So you guys had questions? Yeah. I got that out of my system now. Thanks, guys.
Yeah, under 11, 1.4, number 10.
1.4, number 10.
Disjoint permutations and identity.
Now, is this training, I hope?
Yes.
Hooray. All right. What? 1 point what? Oh, you know what the thing is? You look at 1.4, you're looking at the problems from 1.3, right?
Yeah.
We've all done it. I do it like every time. So if sigma and tau are disjoint in Sn, and sigma tau is equal to the identity permutation, what can you say about sigma and tau? Support your answer. Interesting. What do you guys think?
Immediately, you would think tau is inverse.
Say again? I just say what you said again. I just didn't hear it.
Immediately, you would think that tau is inverse.
Right.
But they have to be disjoint.
But, yeah.
All right.
But
Keep.
on page 58, it says that some elements, a permutation and its inverse are not disjoint, which is basically.
A permutation and its inverse are not disjoint. Right. That is definitely the case because what does a permutation do? It moves the numbers with. If it's not the identity permutation, it moves some numbers, right? And what does the inverse do? It moves that same bucket of numbers within itself, right? I mean, there may be more than one bucket.
Right.
Each bucket, though, moves in a certain way. The inverse moves it the opposite way, right? I mean, that's essentially the thing we learned, is that if we have, sigma is gamma 1, gamma 2, gamma r, then we learn that sigma inverse was gamma 1 inverse, gamma 2 inverse, gamma r inverse. Now, this here, sock, shoes, sock, shoes would seem to suggest that you put the gamma r inverse first, right? But the thing is, if these are, I'm assuming they're disjoint, right? If these are disjoint cycles, then we have this formula for the inverse. But exactly what you said, the inverse permutation moves all the same numbers. The sets which are moved in disjoint are the same for the permutation and the inverse permutation. Getting back to your question, so you got sigma tau is this, right? Number 10? So what do you guys think? Give me an argument. What sigma tau has to be. Did we tell you anything about?
We're told they're disjoint.
They're disjoint.
If they're both,
That's fine.
yeah, but then they're not disjointed, right? If they're both the identity, that would imply.
Well, if they're disjoint, we've proved that this is also what?
Oh yeah, that's the same thing.
Tau sigma, right?
Yeah.
I think you guys are right. Sigma inverse is equal to tau, which says that the set moved by sigma is equal to the set moved by tau by the thing you were just saying, right?
So that's sigma.
So can I say
So sigma must equal tau then.
Oh, I don't think that's true. But you're on the right path. I mean, what did we know? At the beginning of this, these are disjoint. What's that mean? By definition, the set moved by sigma intersect the set moved by tau is what? All right.
Okay.
So both sets have to be just
Yes.
So they can't have anything, which means they're the identity, right?
Right. The identity permutation is the permutation that moves nothing.
Yeah.
Fixes every point, yeah.
Which is
So
disjoint, but it's-
we know that they have to both be equal to the value.
Right.
Okay, so we don't say that the identity, like the identity is disjoint to itself.
Yeah, that's not.
Well, disjoint, but remember, disjoint is not something, I mean,
So,
the definition of disjoint is that the intersection of the sets which are moved is the empty set.
Okay,
And nothing's
that makes sense.
So yes, the one deficiency, if you want to think of it this way, of that definition is that the identity permutation is disjoint from itself. Oh no, it's a horrible definition, but it's okay though, because we don't, I mean, we really shouldn't be talking about the identity permutation when we're thinking about moving stuff around, you know, I mean, it's, yeah. Well, I would say, you know, it's only confusing if you try to assign the natural language meaning of disjoint when you're just like eyeballing formulas, right? But that was not the definition of disjoint. The definition of disjoint was that the moved sets intersect to the empty set. So, other questions?
We can do yours.
Okay. Skipping ahead.
Man, all I do all day is, I just self homework all day long, so all I do is homework. Homework.
Problem number 33. 2.4, number 27.
Wait, I'm sorry, which section we're in?
2.4.
Oh, okay. 2.4, number 27, you say.
I haven't really worked this problem at all. I just know some of our mission problems that I was trying to work on from this section, so I was trying to maybe see a problem in this section.
Ah,
That's okay.
so here I may have to quote things from the future. As in, we haven't formally covered this section yet, obviously, but so we have G a cyclic group. And they tell us that it's generated by G. And what else do we have? We have A generated by G to the power A, and we got B generated by, let me guess, G to the power little b. Yeah, these are indeed, these will be cyclic subgroups by the rights and privileges granted to us thereunto by this section. And so we're supposed to show a, wow, talking about putting the cart before the horse. I don't know if this is the right problem for you guys to look at the moment. I'm going to try, but we may have to bail if it requires too much. If the order of G is infinity, show A is a subset of B if and only if A is equal to QB for some Q and Z. All right. That was if the order of G was infinity, right?
Yes.
And then B is if the order of G is equal to N. Show A is a subset of B. If and only if what? If and only if...
A equals QB mod N.
All right, so A is congruent to QB mod N. Very good. So you guys comfortable with this terminology order? I think I've introduced it, but what that means, just to be clear, this means that G to the N is 1, right? And this means that G to the J is not equal to 1 for all J in the integers minus 0. Phew. Almost forgot to Got to be careful, that 0th power is by definition 1, right? So don't forget about that. Yeah. Let's see here, if and only if. So let's go for it. I'll do this direction because it seems easier to start with. So suppose, right, that A is equal to Q times B, right, for some Q in Z. Then let's see here. We're trying to show that. I guess I should probably mention to you guys the way we define these. This is by definition GA to the K, such that K is an integer, and this is by definition GB to the, let's say, L, such that L is an integer. It's all powers, positive and negative, of the element. Now, so let's see here. What I want to do is I want to pick I'm trying to show A is a subset of B. So let's let X, well, let me not invent new letters. Let's just do it. Let's do it. What is a typical element of A? GA to the K, right? GA is a little bit too special. So GA to the K, an element of A, right? So of course K is an element of Z. All right, so then what? Yep, G to the QB to the K, also known as QB to the QK, also known as an element of B. So A is a subset of B. I'm working on part A right now, obviously. What would the let's look at the same implication in the finite case. I think it's probably productive to do that. So this was part A, right? This is part B I'm doing now. So we're going to suppose what? Suppose A is equal to QB plus let's say Jn for some j in the integers. That's what it means for A to be congruent to B mod n, QB mod n, right? They differ by some multiple of n. And then I need to do what? So I say pick GA to the K in A, and note GA to the K is equal to G to the QB plus N to the K, but by laws of exponents, that's equal to what? Oh, yeah, that's an NJ. My apologies. Let me write that bigger. Sorry. So laws of exponents, that gives me QBK, G to the QBK, times G to the N to the JK. What is G to the N? Well, G to the N by assumption of part A. Oh, did I do this backwards? Part B, I'm in part B, sorry. Part B. Yeah, is 1. So that piece goes away, and what do we have? Right, so we can write that as Q to the, oh, you just told me, Q to the B to the QK, right? Which again is an element of B. Therefore, A is a subset of B. So whether it's finite order or infinite order, either way, the assumption that, so what do we have here? Another way to, I mean, let's see here, how to say this. Okay. Yeah. I mean, we could try to do the other directions if you wanted.
Can we do one?
Okay, I think we'll do the finite one. How about that? Other way. So what should we assume? The order of G is n, and A is a subset of B, right? And we're still, A and B are so defined, right? So A is this, right? B is that. And what else are we assuming? Oh, that's it, right? Now, what we want to show, that A is congruent to QB mod n, right? So let's see here. The piece of data that we're given, the thing we should try to like extract information from here, most notably, I think, is this, right? So this is something there's almost, I would say it's something that's shown in the section, but it's also just kind of like duh. This is an element of the set generated by GA in particular. Take k equal to 1, it's in there, right? So the cyclic subgroup generated by GA contains GA. Go figure. Now, this is a subset of B, right? Which is equal to this thing, right? So to be clear, GA has to be an element of the cyclic subgroup generated by G to the power B. What's that mean? Right, there exists, would you guys tell me J? Use a J? They hear J? There exists J in the integers such that what? GA is equal to what? GB, K? All right, we can do that. GB to the K, sure, why not? Right? So, what? So what this then means is that GA to the minus BK is equal to 1. By laws of exponents, that implies that.
So then A minus BK is equal to n.
No, actually, what we get. So what the theorem we prove, a theorem that we prove in this section, is that if the order of G is equal to n, and G to the D is equal to 1, then n divides D. So like, if I'm working in, for example, like if I'm working in Z20, right? And, oh, I'm sorry, forget that. Suppose I'm working in C4, and I have something like G to the D equals to 1. That means that 4 must divide D. That means that D has to be equal to something like 4, or 8, or 12, or 0, or minus 4, etc. D has to be a multiple of n. So, in short, when I get this implies that A minus BK has to be equal to n times j for some j. It has to be a multiple of n. Which, of course, says what? That says that A is congruent to BK mod n. I see now that we should have called that KQ. Oh well. The logic should be clear if the letters are not. That is one of the major theorems in this section is this, that if you have an element to a power, that power has to be a multiple of the order of the element. Yeah.
That helps. I just know after, I think, maybe problem, like the fourth problem in the mission, that they allow to start coming from this section. So
Yeah, yeah.
So Thursday's not a really long day.
Figure number 21. Let's see, it's 2.2 number 12.
2.2 number 12. Two point two number 12.
Yeah.
So you've got G a group, order 4. 1, A, and B are distinct elements of G. A squared is 1, B squared is 1. Show that. Oh. Yeah, this is kind of, I mean, this is pretty much just like a process of elimination problem. Not especially exciting. I think, so how does the logic go here? We're,
A squared is 1, B squared is 1.
so we're also given that the group has order 4, right? So this might, I mean, let me write. I guess this AB is not, I mean, that we should explain why that is. So I got 1, A, B, A squared is 1, B squared is 1, right? And then the question is what else happens, right? So if we think about A times B, right? If this is equal to A or B, right? What is that? If it's equal to A, what does that say? Why can it not be that?
Because B is equal to 1.
Right, by cancellation, that implies B is equal to 1. But B is not 1, right? And likewise, if we have AB equal to B, that implies A is equal to 1. Also a trouble because A is not 1. Right? And A and B, A times B cannot be, why can't AB be equal to 1?
A would equal
Oh, so your point is that this is equal to A. I agree with you, but let me write down more. So that is also equal to A squared, which by cancellation implies that B is equal to A. Oh no, but A and B are distinct. So these three options are not available to us. It must be that AB is a new element. And so that's, I think, one of the main points to this problem is to make that argument I just made. Okay? So once you do that, then of course this is for free. Now BA has to be equal to AB. Why? Otherwise it'd be a new element. And it cannot be A, B, or 1, because if it is, by cancellation, we get that one of those is 1, that it's not 1. So this has to be AB again, because otherwise we'd have more than 4 elements, but we're told that it has 4 elements. That has to be AB again. And then, so that's AB, this is AB. And then what else happens? A times AB is B. This ABA is AAB, so that's B. Process of elimination, that has to be A. Process of elimination, that has to be A. And then this has to be 1, right? So, yeah. I'm sure you could fill a page full of sentences explaining all of the nuanced bit by bit, step by step thinking there, but.
And there can always only be one of each element, and like two of those can count.
Right, that was a theorem we had in this section. Is there a cyclic group problem that I could help you guys, that I could work that would help you with the mission? Like which problem have I assigned in the mission that will help me? I can pick an example out to help you guys. Like 2.4 problem? Did I have a problem in 2.4?
2.4 number 13 is that Wilson's theorem thing. I think that was one of
And then you're saying 31 too.
no, that's a really good one.
So I've assigned 13 and 31, you said?
Yes, 13 and 31. What you said. Problem 17 is, I think, would be from that section, but you wrote it. Suppose G and H are cyclic groups with relatively prime orders. Prove that G cross H is cyclic. I think what you did with that last question that I asked was definitely helpful.
Oh yeah, for that least common multiple one. Sure.
Yeah.
Yeah, the same sort of,
Yeah.
the technology needed for that problem is the technology I was showing you for this problem, right? And we're talking about 31, right?
Yeah.
Um,
Because it looks similar with the A.
Let's-
has order equal to infinity, the other one has order equal to n, so I'm guessing we use similar logic.
yeah. So you're trying to show set equality, right? So you probably want to show double containment. I mean, you start by, I would my gut reaction to this problem is to show that A intersect B is a subset of the group generated by GM for number 31. You say, okay, I'm given A, I'm given B. I let M be the least common multiple of A and B, right? And then I pick a point in the intersection of A and B, right? So that means that it's both a power of, it's both a power of GA and it's both a power of GB,
Which means it's in GA and GB.
right? Because it's in the intersection. So
Right, that's just showing.
then you got to somehow look at that, tilt your head and quit and go, aha! That means that this power is also a least common multiple of A and B, so it's a multiple of M, which shows that it's in the, the group generated by G to the power M, M being the least common multiple. And they go the other direction. What does it mean for it to be a least common multiple? It means that M is equal to J times A. It's also equal to B times K, right? And so if those things are true, then you ought to be able to take an arbitrary GM to the power P and rewrite it as GA to a power or GB to a power, and in fact both, showing that it's attained in both kinds of powers will then show that it's in the intersection of the cyclic groups generated by GA and GB. So I think part A isn't that bad. And part B, it's going to be just the kind of thing we were wrestling with over here. So, yeah.
Oh, this is Wilson's theorem.
Wilson's theorem, yes. Let's see here. Part A, we've got that G1 through GR is an abelian group, right? And A is the, aha, ho ho ho.
Guessing that means challenging.
Why don't we just take an example and see what happens, right? How about this? C4 has served us well so far, right? This is an abelian group. Oh, K4, let's be all fancy about it. Right? Wait a minute, was there anything else? No, that was it, right? That was the Klein 4 group. 1 ABC, right?
Yeah.
Is this abelian? Yes, the Klein 4 group commutes.
Yeah.
So this, what he says in this problem is to look at a group, right, where you've got G1, G2, gr, is that right? I mean, I may be, and he says just what does he call the product of all of them? X or what?
A.
Oh, A. Okay, A. G1, G2, I mean, you call it whatever you want, right?
Yeah.
But he says if you multiply them all together, then A squared is equal to 1, right? That's the first part. That's the first thing you got to prove. All right. Why is that true for this one? If I take A, B, C times A, B, C, what happens? It's commutative, right? It's commutative, so we move things around. So we get A, B, B, C, C. Because we can move the things around so that they're next to their inverse, right?
Just as it's commutative.
And it's a group, so everything has inverse.
So whatever's in here, you square it, right? You got G1, G2, da da, GR, G1, G2, da da, GR, right?
Yeah.
I mean, you got to think about a notation which expresses that concisely, but so it's commutative. We can move it around so that the element and its inverse are paired, and we get then 1 times 1 times 1. All right. So that looks way scarier than it is, right?
The
Yeah.
second part that I'm might just be confused on notation.
So there, we are supposed to prove that p minus 1 factorial is congruent to minus 1 mod p, where p is a prime.
Looks also as complicated just looking at
And then he's like, hint, something you don't quite understand yet,
Exactly.
zp star. So let's chase that whirlwind. Let's see here. So zp, what does z prime star look like? Prime. So what's the greatest common divisor of k with p?
Always
It's 1 for k equal to 1, 2, all the way out to p minus 1, right? So that means that 1, 2, 3, da da da, p minus 1. These are all what? I'm sorry. These are all units, right? In other words, everything in this list has an inverse in this list.
So then when you do factorial, then it should be commutative, right?
Right, this is a two-part problem. So your first hint is that you did part A, right?
Yeah.
So maybe we should look at part A applied to that.
So we want to show that that's
It is, I mean, that's abelian.
right, so we don't have to show that, okay.
So then we want to show that.
What happens when you look at the product of all the elements of ZP star?
Should equal.
Yeah, it's supposed to be congruent to 1 at least, yeah. I mean, it's supposed to, if I put bars. So 1 bar times 2 bar times 3 bar, da da da, p minus 1 bar, and then again, right?
Yeah.
Wait, what are we doing there?
Because that's part A. Our part A said take everything in there
Oh.
and square it. That's A. This is A again. That's 1 bar, right? But what is that? Hmm.
Do we have to start with it squared then? That's what that-
Yeah, I mean, I don't know if it's, I mean, I'm assuming that might be helpful. I could be wrong, but, oh,
You would think of the A and B.
what else, what is that? I mean, equivalently, we could also, this also says what? A is equal to minus, is equal to A inverse, right? Maybe you're thinking of going with that?
Sure, yeah.
I don't know if that's helpful or not. I don't know. I mean, I will say this much is obvious, right? If you pick off this is 1 times 2 times 3, da 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 da, p minus 1, congruent, right? AKA this, just half of it is p minus 1 factorial congruent.
So p minus 1 factorial squared is equal to,
1 5.
well, yeah.
Hmm.
Congruent to
Yes, so p minus 1,
we're
P-
trying to get
P-
negative 1.
p minus 1 factorial squared
1
Is-
is congruent to minus 1 mod
Wait,
p.
why can we say minus 1?
That's the problem.
Oh,
It's not obvious yet.
yeah.
We're looking for,
I mean, from this calculation in part A, all we have to say at the moment is that this p minus 1 factorial, whatever it is, the congruence class, that squared is equal to 1, right? I'm sorry, minus 1. Wait a minute, did we say that?
Wait,
No.
no, I don't
Oh,
think it's
just 1.
we
1.
say
We say 1.
We just show
We want to show that, yeah.
show that it's congruent to minus.
Interesting. Oh, I'm sorry, I seem to have kept you guys over.
P minus 1 factorial squared is equal to 1, and it's its own inverse. So P minus 1 factorial has to be either 1 or negative 1, right?
Hmm.
Or two digits.
Did we prove that?
Are we saying it's definitely equal to 1, or are we?
Yeah,
Well, I mean, the part
comment from A that it's equal to 1.
from part A applied to the zp, the units of z mod p, yeah.
Yeah, so that means P minus 1 factorial bar is equal to its inverse.
The question then is, why is that p minus 1 factorial congruent to minus 1?
Because it could be positive 1 or minus 1.
Does algebra work that way in Zn? I mean, you need to work through it. It's definitely a solution, right?
Right. We'd have to show that it's not.
I mean, minus, yeah,
It
if,
has to be its own inverse.
Yeah, we should above that.
so it seems like we should come to a complete and like good understanding of what are the solutions to the quadratic equation x squared if we solve x squared equals to 1 in z mod p, what are the solutions, right? If you come to an understanding of that, then it should settle this question for you. I feel like we might have done that before, which you might be talking about, but I can't remember for sure.
I've done this in a few classes.
That is true. When I taught number theory once upon a time, this came up in there. I think I did it in class, actually.
That's why I'm like trying to think. I'm like, I know I've done this.
You can, I think we're done. Yeah. Yep, hit the, that's all, folks.